All right, we did a growth decay model where you knew the growth constant or the growth, rate. Let's do one where we do not know the growth rate. So you're told that the half-life of radium-224 is approximately 4 days. And what that means is it takes 4 days for a sample to decay by half. All right, so whatever you start with, whether you start with 1 gram or 100 grams or 29.7 grams, it's going to take 4 days for half of it to be gone. So if you start with 1 gram, in 4 days you have half a gram left. If you start with 100, then in 4 days you have 50 grams left. If you start with 22, in 4 days you have 11 grams. All right? So construct the decay model for a sample. Round A to 6 decimal places. All right. So let's try this. Here's what I know. Whether you use P or A or whatever, it doesn't matter. Right, this is my growth and decay model. Some initial amount times growth rate raised to the t. T is in days. Okay. Well, if I want to look for A, then I need to fill in, I need to know an A of t, and I need to know an A naught, and I need to know a t, because otherwise I would have too many unknowns. So if I did have all of those known, then I would be able to find A. Okay. So because I know the half-life is 4 days, so suppose we start with 10 grams, then in 4 days there is half, or 5 grams left. This is what I need. So we start with 10, so that's going to be my A naught. 4 days, that means that's my time. 5 grams left, that's my population at time. So now the only thing I don't have is A. Alright, so I have 5 grams, I start with 10 grams, I have an unknown growth, and it's raised to the 4th power. So I need to isolate, just like regular equations, you need to isolate your variable of interest, which in this case is A. So I'm going to divide both sides by 10, which gives me 5 over 10 is a to the 4, and 5 over 10 is a half. So no matter what amount I start with, when I divide and isolate my A, I always get 1/2 on this side because it's the half-life. Alright, so if I want to solve for this, I'm going to take a root, right? What root? 4th root. Alright, 4th root of 1/2. When you go to calculate this, you can use the 4th root, or you can say thing to the 1/4 power, because remember, reciprocal powers make roots. All right, so on my 4th root button, that's on mine, it's here. So I would say 4th root of 0.5, which gives me 0.8408, and said 6 decimal places, right? So 1, 2, 3, 4, 5, 6. So 0.840896. Or I could write 0.5 to the 1/4 power. You can either write it as 0.25 or you could write it as 1/4. Same thing, 0.8408964153. All right, so that's my A, which means A of t is A naught 0.840896 raised to the t power. In order to find this A, I needed a piece of information that would fill in every other part of my model. So I needed to have something about the initial and then something about the population after a certain amount of time. And that's what the half-life gave me. So they ask, I didn't say how much to round. They want you to round to 3 decimal places on both B and C. Okay, so B asks how many grams of a 5-gram sample remains after 9 days. Well, we're just going to be able to plug in, but let's stop and think. 9 is much larger than my half-life of 4. It's more than double. So what I'm expecting is there's not a lot left. Certainly less than 2.5. Should be less than 1, right? Because half and then another, roughly another half. Now as you lose part of your sample, it does grow or decay a little bit slower, but I'd still like to see, you know, roughly another half of it gone. Okay, so, you know, maybe about quartered. All right, so for t equals 9, we want A at 9, so I'm going to plug, oh wait, let me comment on this. So this is a function. In goes number of days, out comes grams of radium 224. All right, so I'm looking for how much is left after 9 days of how much? A 5-gram sample. So in this case, they had to tell me how much I was starting with. So I'm starting with 5 grams. I've got my 0.840896 raised to the 4th power. And this is just calculator at this point. You can punch this in. You actually can store stuff. Sometimes like in variables, or let me think, so that you don't have to type it in all the time. I'm not sure how to do it on this pink calculator. I think on this one, so 0.840896. I hit the, and they all work roughly like this, but the syntax maybe is slightly different. I hit the store button and it draws a little arrow for me, and I tell it where I want to put it. I'm going to put it right here on the key that has just a list of variables. So I store it to X and I hit enter and it's stored. So now if I want to do like 2 times that thing, I just hit 2 times X and it does it for me. I don't have to type it all out. Okay, so that's nice because now I can do 5 times my A raised to, oh, here's an example of the caret. So this calculator has a caret key instead of a power or exponent block like my other one. To the 4th power, enter, that's 2.49. Oh, sorry. This should be 9. So if I plugged in 4 here, I got 2.5. That's half, right? Well, yeah. That was my half-life. Here I am at about half. Okay, sorry. This should be 9. All right, so 5 times my growth rate raised to the 9th power, I have 1.051. It said round to 3 decimal places, so this is grams. All right, and then you're asked how much is left after uh, 2 days. So now I'm doing t equals 2. My initial is 5 grams. I'm looking at A at 2. Is 5 times 0.840896 raised to the 2nd power. So 5 times my constant raised to the 2nd, which is 3.536 grams. So round to 3 decimal places, this 5 goes to a 6. All right, so if you know the half-life, then you already know whether this should be bigger, these numbers should be bigger or smaller than half of your original sample, depending on if they occur before or after that half-life. We needed some piece of information in order to solve for that constant so that we could plug in something for everything except for the A.